So in this video I want to go through how we can use calculus techniques and other ideas to produce a sketch of the following function. It's a function of a variable t, and the function is t squared divided by t plus 3. So this is an improper rational function. So let's draw a set of axes, and then we're going to think at the side about some simple ideas to do with the function and start our graph that way. So our axes are labelled t and y. So one of the first things that we can do is we can think about what the value of the function is when t is equal to 0. So when t is equal to 0, what we have is that our function f of 0 is equal to 0 divided by 3, which is equal to 0. So we see that our function is going to pass through the origin. So I'm just putting a dot here, a red dot, to remind me. We can look at our rational function and we realise that if t is equal to minus 3, we would be dividing by 0. If t is equal to minus 3, the numerator is 9, we would have 9 divided by 0. So we conclude that this function does not exist when t is equal to minus 3. So, as we're just saying, at t equals minus 3, our function f of minus 3 does not exist. So this corresponds in terms of the graph of the function to a dashed vertical line at t being equal to minus 3, and our function does not exist there. So this line is going to be a vertical asymptote, and we're going to have to think about as it approaches it from the right, whether it approaches it this way or this way, and we're going to have to think about as it approaches it from the left, whether it approaches it this way or this way. So let's think about that. Well, if we look at our function again, t squared is always positive. And if we look at t plus 3, we realise that if t is a little bit to the right of minus 3, so we have something which is a little bit to the right of minus 3, t plus 3 is going to be positive. So we're going to have something positive, t squared, divided by something small and positive, so we are going to get a large and positive value. So this is roughly what our asymptote is going to look like. Similarly, for t being to the left of the line minus 3, the numerator is positive, but t plus 3 is going to be negative in this region here. So we're going to have something negative. Not only that, we can also recognise that for t greater than minus 3, this is always positive, so everywhere here to the right of the line minus 3, our function is going to be positive, or at smallest, it can be 0 when t is equal to 0, and that's what we've seen here. So actually we can immediately realise that this is going to be a minimum, which we will verify using calculus techniques in a moment, and that our function is going to have to look something like it comes down to here, there's a minimum, and then it's going to go up again. Similarly here, to the left of the line t is minus 3, we know that our function is going to always have to be negative, because we have something positive, t squared, divided by something which will be negative for all t to the left of the line minus 3. So, in other words, what we can do is we can realise that our function is always going to be somewhere in this region here, and it's always going to be somewhere in this region here, And what we have to do is to work out exactly how it's going to behave and what's going to happen to it here. The next thing that we can think about for our function, perhaps before we turn to calculus techniques, is to ask ourselves what's going to happen as t, our variable, approaches plus or minus infinity. And for this, for a rational function, it's extremely helpful to rewrite our function in the following way. So we have f of t is t squared divided by t plus 3. And what we do is we look at the largest power in the numerator and the largest power in the denominator, and we take the smaller of those two largest powers. In this case, it's t to the 1. And we divide the whole of the top and the whole of the bottom by that largest power. So we have, in the numerator, we're dividing by t, we get t. And in the denominator, we're dividing by t, we have 1 plus 3 over t. And doing this has not changed anything. We've just divided top and bottom by t, and we have an exact algebraic equality. The reason why we've done this is because we're interested in understanding what happens for very large values of t. And we realize now, from looking at this form here, that as t becomes very large positive or negative, 3 over t is going to approach 0. So therefore, f of t is going to approach t over 1 plus 0. In other words, it's going to approach t. So this tells us that for very large values of t, the line y equals t, that I'm roughly sketching here, y equals t, is going to be an asymptotic line that our curve will approach. So we have a lot of information about our function. We realize that as t approaches infinity, it's going to approach here, and as t approaches minus infinity, it's also going to approach here. But now what we need to do is to study the extreme values, the stationary points of this function, look for where it can have maxima and minima, and that will help us to complete our graph. So what I'm going to do is move on to the next slide, roughly sketch what we have from here, differentiate our function, and look for stationary points. So I'll do that on the next slide. So what I want to do now is to calculate the first derivative of our function and look for when that first derivative vanishes. So what we find is that the first derivative, I'm just going to use dash notation here, is going to be, and I'm going to use the product rule together with the chain rule for powers, so I have t squared multiplied by t plus 3 all to the minus 1. The derivative of t squared is 2t, and that's all multiplied by t plus 3 to the minus 1, so it's just on the bottom. And then for the next term, I'm going to get t plus 3 to the minus 1. When I differentiate it, I pull down the minus sign. The t squared factor is already sitting there. I divide them by t plus 3 all squared, because I have to lower the power by 1, and minus 1 is minus 2. And then this is multiplied by 1, because the derivative of t plus 3 with respect to t is just a 1. So I have that, and I want to put this on a common denominator, and I'll leave it for you to verify, but the common denominator is clearly going to be t plus 3 all squared. That's the lowest common denominator. And when I put these two terms together, what I'm going to find is t squared plus 6t. Now, what I want to do is to realize when this vanishes. And it's important that I pick up every term where it vanishes. So to do that, if I look at the numerator, for my first derivative, I want to factorize the numerator here. And this is, fortunately, very easy to factorize. It is a factor of t here and here. So I have a t multiplying a t plus 6, all divided by t plus 3, all squared. Now there is no finite value of t for which the denominator approaches infinity, apart from where t is equal to minus 3, and we've already seen that the function itself does not exist there. So the only places where this is going to vanish, where we might have a maximum or minimum, is when t is equal to 0 and when t is equal to minus 6. So therefore we see that we have stationary points at t is equal to 0, and if t is equal to 0, the function evaluated at 0 is 0 over 3, so as we've seen, it goes through the origin. And that's exactly what we anticipated previously. We know that the function is positive here, we know it comes down to here, so it is going to have to come down here and then go up again, so this must be a minimum. So we have a stationary point there, and we have another stationary point when t is equal to minus 6, and if we substitute minus 6 into our function here, we get plus 36 when you square minus 6, and then we have minus 6 plus 3, that's minus 3, so we have 36 divided by minus 3, and that is going to be minus 12. So our minimum here is, our minimum is at the origin here, and here we know that our function approaches minus infinity here, and we have another stationary point at minus 6, so that's going to be around here, and when y is equal to minus 12, so that's going to be somewhere around, let's say, roughly here. Let me just try to draw it in. So a point around here, say. And that, again, just looking at the graph, is going to have to be a maximum. So our function comes down to here, has a minimum value and starts to go up again. Our function goes down to here, hits a maximum value at this point with coordinates minus 6, minus 12, and it's then going to go down again. These are the only two stationary points. So that means that our function cannot turn over again because there would have to be another maximum value. And we've seen that the function approaches y as t for very large values of t. So it must be the case that our function does something like this. And again here, on this side, it cannot go up or anything like that because there would have to be another minimum, and we know that this and this are the only 2 points where the first derivative vanishes, and the function exists certainly for all t less than minus 3. So it must be the case that our function is going to approach the line y equals t in this way. And let me mark onto the graph the important values that we have. This is minus 6, and here we have minus 12. So this is the sketch of our function, and our function f of t is t squared over t plus 3. And we don't really even need to calculate the second derivatives to show that this is a minimum and that this point here with these coordinates is a maximum. We've really completed the sketch. However, for completeness, on the next slide I will just calculate the second derivatives and show that here at this minimum our second derivative is positive, and that here at the maximum our second derivative is negative. So what we've seen on the previous slide was that the first derivative of our function is t squared plus 6t over t plus 3 all squared. And we've also seen that the first derivative vanished at t is 0 and t is minus 6. What I now want to do is to calculate the second derivative of the function, in other words the derivative of this, and then just check its sign at t is 0 and at t is minus 6. So the second derivative of our function is of course the first derivative of the first derivative, the first derivative of the derivative. So it is the derivative of t squared plus 6t over t plus 3 all squared. So I'm going to do this again using the product rule together with the chain rule for powers. So I think of this as t squared plus 6t multiplied by t plus 3 to the power of minus 2, because this is in the denominator. So what I'm going to get, therefore, is when I differentiate the first term, the numerator, I get 2t plus 6 over t plus 3 all squared. And then when I differentiate the second term in our product, the t plus 3 to the power of minus 2, I'm going to have plus t squared plus 6t multiplied by the derivative with respect to t of t plus 3 all to the power of minus 2. And now we notice the following. At t is equal to 0, this will vanish. At t is equal to minus 6, this will vanish. This is not surprising. These are the values where our first derivative vanished, and our first derivative vanished because this factor was 0. So again here, this factor is going to vanish, and this whole term will vanish at t is 0 and t is minus 6. The only way that might not be the case is if differentiating this was going to give us a factor in the denominator of t or of t plus 6, and it clearly is not going to do that. So this term here is going to vanish, all of this term is going to vanish at both of our extreme values, both of our stationary points. So what we see is the following. At t equals 0, our second derivative of the function with respect to t, evaluated at t is 0, is going to be, well, from this term here, I'm going to have 2 times 0, which is 0 plus 6. So I'm going to have 6 over 0 plus 3 all squared is 9. And this is positive, it is greater than 0. So therefore, at t equals 0, we have the function's first derivative vanishing, and its second derivative is positive. So this, therefore, corresponds to a minimum. What about at t equal minus 6? The second derivative with respect to t, evaluated at t equals minus 6, is going to be, well, from the numerator we have 2t plus 6, so that is minus 12 plus 6, so we're going to get minus 6. And on the bottom we have minus 6 plus 3, so that is minus 3, all squared, that's going to give us plus 9. So we get minus 6 over 9. This is negative, and since it is negative, we therefore recognize that this is a maximum. And that is, of course, exactly what we'd realized in our previous sketch, but it's been useful for us to check it, and it's given us some further examples of using the product rule together with the chain rule for powers in place of using the quotient rule. So at this stage I will stop the video and move on.